Hi, last time we learned that the n-dimensional Fourier transform can be written in terms of n over 2-dimensional Fourier transform. So f of n is equal to a block matrix of the form fn over 2 on these two components, and there is a n over 2-dimensional diagonal matrix. And then, of course, there is a permutation matrix, Pn, where Pn transpose is equal to E0, E2, and all the even standard basis vectors, and then the odd standard basis vectors. All right, so let's take an example of um, 8-dimensional Fourier transform, and let's apply this to a vector x of 8. And let's see how this works out, this particular theorem works out. So x8 is an 8-dimensional vector, which is given by x0, x1, x2, all the way till x7. Okay. And so we need to compute this. So this is going to be equal to f4, f4, d4, f4, and minus d4, f4, where d4 is a diagonal matrix, 4-dimensional diagonal matrix, and then there is p4 applied to x8. Right? So p4 applied to x8, p4, p8 applied to x8. So this is going to be p8 applied to x8. So p8 applied to x8 will just get all the even terms together, even components too. So this will be x2, x0, x2, x4, x6, and then followed by x1, x3, x5, and x7. Right? So I can write this as x4 of 0 and then x4 of 1. Right? Where x4 of 0 is all the even entries, and x4 of 1 are all the odd entries. Right? So, okay, so we need to compute f8 of x8. So f8 of x8 is equal to f4 d4, sorry, f4, then f4 d4, f4 minus d4, f4 applied to x4 of 0 and x4 of 1. So this is going to be equal to f4 x4 of 0. This will be a 4 cross 1 vector plus d4 f4 of x4 of 1. And then on the bottom, there will be another 4 cross 1 vector to make it a 8 cross 1 vector, f4 x4 of 0 minus d4 f4 of x4 of 1. Okay, so that's step number 1. Now we can recursively do this. So let's see how we can do this. So now we have to compute f4 x4 of 0, which is this, and f4 x4 of 1, right? both the numerator and the denominator over here just contain these entries, right? So let's see how we can compute F4 x4 of 0, and we'll also compute F4 x4 of 1. So again, using the theorem, x4 of 0 is equal to F2 x2 D2. This is a 2 cross 1, 2 cross 2 diagonal matrix. X F2 minus D2 F2 and P4 of x4 of 0. Similarly, F4 x4 of 1 is equal to F2 D2 F2 minus D2 F2 and P4 x4 of 1. Right? Now, P4 x4 of 0 interchanges the even and odd entries of x4 of 0. But x4 of 0 is just, we just computed it. It's over here. So it will interchange, P4 x4 of 0 will interchange, it will get these two together. So, and then it will get these two together, right? So therefore, P4 x4 of 0, I can write as x2 of 0, x2 of 1, where x2 of 0 is just x0, x0 and x4, and this is x2 and x6, right? And P4 x4 of 1 is equal to, let me call that x2 of 1, x2 of 2, and x2 of 3, where x2 of 2 is x1 and then x5, and this will be x3, x7, right? So let's do this calculation. So F4 x4 of 0 is F2, this matrix, 4 cross 4 matrix, D2 F2 minus D2 F2 applied to x2 of 0, x2 of 1, and then F4 x4 of 1 will be equal to F2 D2 F2 minus D2 F2 applied to x2 of 2, x2 of 3. So we get two components over here. Sorry, this is going to be F2 D2 F2 x2 of 0 plus D2 F2 of x2 of 1, and then F2 x2 of 0 minus D2 F2 of x2 of 1. This will be F4 x4 of 0, and then F4 x4 of 1 will be equal to F2 x2 of 2 plus D2 F2 of x2 of 3, and F2 x2 of 2 minus D2 F2 of x2 of 3. All right. And then finally, we have to compute these F2 x2 of 0 f2 x2 of 1, f2 x2 of 2, and f2 x2 of 3. So, but we know that f2 is equal to 1, 1, 1, minus 1, this matrix. So these are quite easy to compute. When you want to compute the 8-dimensional Fourier transform, you start at this level, which is multiplying a 2 cross 2 matrix with a 2 cross 1 vectors. There are 4 vectors to be computed at level, let me call it level 3. Then there are these 2 vectors to be computed at level 2. And finally, there are using those 2 vectors, we are computing this 1 vector at level 1, right? So let's one can draw the picture in the following way. If you want, you can. So you have to compute f2 x2 of 0, f2 x2 of 1, f2 x2 of 2, and f2 x2 of 3 at the first level. Then using this, you have to compute f4 x4 of 0, these 2 vectors, f4 x4 of 1, and then finally using this, you have to compute f8 x8, right? So but notice that one thing to notice is that uh, the vectors to be computed at this level have a little a permutation that looks like this. So x8, suppose x8 is x0, x1, x2, x3, x4, x5, x6, and x7. Then I'll call this x8 twiddle is equal to x 0, x4, x2, x6, and x1, x5, x3, x7, right? Because if I look at this is x2 of 0, x2 of 1, x2 of 2, and this is x2 of 3. Right? So therefore, there is some permutation of this going on. And so when you start initially, the initial permutation is essentially what is known as the perfect shuffle. So if I have 1, 2, 3, 4, 5, 6, 7, 8, then the first is an exchange bit or getting all the even. So I should write it in the way we are doing. I should write it as 0, 1, 2, 3, 4, 5, 6, 7. The first is to get all the even and odd terms together. So that is the first step. And then 1, 3, 5, 7. And within this, so this is the first. And then within this, you sort of do again even and odd shuffle. So this is 0, 4, 2, 6, and this is 1, 5, 3, 7. So this is the permutation of the original. So before you start working backwards, you have to do the permutation of the, which is known as the perfect shuffle. So this is a perfect shuffle. And to obtain this, well, it's the way to do it, and it's a neat way of doing it. So you write the original indices in binary form. So this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And this is 1, 0, 0, 1, 0, 1, and then 1, 1, 0, and 1, 1, 1. So this is 0, 1, 2, 3, 4, 5, 6, and 7. And so, the perfect shuffle can be obtained. The perfect shuffle can be obtained by just the bit reversal. So I'll just take the bit reversal of all these bits. So this is 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, and 1, 1, 1. So this is 0, 4, 2, 6, 1, 5, 3, 7. So we have obtained by just, so it's a neat trick to obtain the initial permutation. Okay, and finally we want to talk about how many operations. So we are doing this to reduce the number of operations of the Fourier transform from n log n to from order of n square to order of n log n. And so if I look at this picture over here, so there are so let's take n to equal to 2 to the r, and there are let's say there are r levels over here, right? And we want to see how the computations or how many multiplications are there at each level. Okay, so if I so first let's figure out how many of these components are there. So I will call this as a component, right? So this is one component. So at if I take the level, this is level 1, this is level 2, and this is level 3. So there are R levels. So at each level, there are how many components? 2 to the uh, R minus J, where, right? So at level 1, so for R is equal to uh, 3 and J equal to 1, there are 3 minus 1, that is 2 to the power 2 components. So at each level, there are 2 to the J, R minus J components to compute. So over here, for example, there are 2 to the 3 minus 2, which is 2 components. Over here, there are 2 to the r minus 3 or 3 minus 3, which is 1 component. So, and at each level, how many multiplications are there? So over here, for example, I can check that if I go over here, right? So if I want to compute f4 x4 of 0, then the multiplications are involved over here, right? This, right? And over here, right? So there are multiplications are over here. This is the multiplications of a 2 cross 2 matrix with a 2 cross 1 vector. So how many multiplications are there? So over here, there are at each level, there are 2 to the j minus 1 multiply. At level j, there are 2 to the j minus 1 multiplications. For example, at this level, um, since I'm multiplying a 2 cross 2 matrix, right, with a 2 cross 1 vector, there are 2 multiplications, right? At this level, at the higher level, over here, there is a 4 cross 4 matrix multiplied by a 4 cross 1 vector, right? So there are four multiplications, right? For example, and that happens because this is a diagonal matrix. D4 is just some 1 eta, eta square, eta cube, right? That is D4. And then when I multiply it by some vector, which is a 4 cross 1, so x0, x1, x2, x3, then there are 4 multiplications, right? So therefore, that at each level, there are 2 to the j minus 1 multiplications. So 2 to the j minus 1 times 2 to the r minus 1 I minus j components is equal to 2 to the r minus 1 multiplications at each and every level. And there are r levels. So therefore, we get r into 2 to the r minus 1 multiplications. that is equal to n over 2 log n. So that's how you get the n log n benefit of the fast Fourier transform. Once again, summarizing this last part. So there are R levels once we decompose the Fourier matrix into sub-matrices and do that recursively. We get R levels where n is equal to 2 to the power R. And at each level, there are 2 to the R minus 1 multiplications because there are 2 to the R minus j components, and each component is using 2 to the j minus 1 multiplications, right? So you get this order of n log n efficiency of the fast Fourier transform. All right. Thank you.